Okay, happy Friday. Looks like it's supposed to be a nice weekend, so get out there and enjoy it, but spend a lot of time on statistics too. All right? Come on, man. What could be more fun than it? I know that. Do this. Do your statistics outside. How about that? Any questions over section 11.2? 11.2 was... What was 11.2? No, not the chi-square, not the chi-square test. That was the one before. Last time was two sample t-test. That's right. 2 sample t-test, which was like this. This is today. 2 population means, sigma unknown, but last time was independent samples. Now it's dependent samples. So what does dependent samples mean?
Not Indian.
How do you know when you have dependent samples?
It's the same population.
It's the same subjects measured twice. That's typically what we have when we have dependent samples. Paired samples. There's some natural way to pair them together, right? So it'll be before and after readings. It'll be, measured under this condition, then measured under a different condition. Something like that. Okay? We've had this situation before when we did confidence intervals. Do you remember what the main difference is? What do you... Can I start that sentence over?
No.
What do you do different for dependent samples than you do for independent samples? In other words, what's important? You take the... What? No. This is still T. You take the difference between the after and the before reading, or whatever it is, right? So you got 2 samples, call them sample 1, sample 2. Then within each individual, each pair, you take the difference. And it's the differences that are important. So there's really nothing new in this section from when we did 1 sample means problems. You got 2 samples, but they're paired. So you take the differences and you create 1 sample of differences. Now you got a 1 sample means problem instead of a 2 sample means problem. But it's on the differences. So we just use notation is a little bit different. We use D's instead of 1s and 2s. And instead of X bar, we have D bar. Instead of S sub X, we got S sub D. All of that. But otherwise, all the formulas and everything are the same. So here are the assumptions needed for a paired 2 sample means problem. First of all, the samples have to be random. We always have that. Samples are dependent or paired. Both population standard deviations are unknown. And then either the number of pairs is at least 30 or the distribution of the differences is approximately normal. You know what my grandpa would have said? You sound like a jackass in a tin barn. Yeah, he was from Kansas. My dad would have said a bull in a china shop or something like that. So take your pick of metaphors. Now, this book does a convention on those differences. They say, let's impose a rule that in situations where we have measurements taken before and after some treatment, the measurement is taken after treatment is contained in population 2, and thus it will always be the first value in the subtraction. So that's a completely arbitrary designation, but it's done for consistency, and it helps you kind of remember what to do. I don't care. For me, it doesn't matter which direction you do your subtraction as long as you know how to set up the hypotheses accordingly. So if they make a statement like, after they take this new medication, does their cholesterol go down? Then you understand okay, which direction did I do my subtraction, and what does go down mean? All right? So it's either greater than a negative number or it's less than a positive number. It doesn't matter. They use the convention to always do the subtraction in the same direction with before minus after. Right? Before minus after. So they will always use the convention mu2 minus mu1, where this is after and this is before. Like I say, on the test next Friday, it won't matter as long as you set it up. You can do the subtraction whatever direction you want as long as you set everything up and work it correct after that. But on the online homework, they will get picky about what your null and alternative are because you may do the subtraction in the opposite way. They'll count that wrong. Right? So we'll need to practice this a little bit. Let's practice with this one. The manufacturer of a new diet pill claims that the pill helps a person lose, on average, more than 7 pounds in the first week. To test this claim, 15 people volunteer to take the pill for 1 week. Their weights are measured at the beginning and end of the week. State the null and alternative hypotheses for this test. What's the convention say? That sample 2 is the after, sample 1 is the before, and we're going to do the subtraction in this direction. Okay? So let's look at that claim. They claim the new diet pill will help a person lose more than 7 pounds. Is that statement a null or alternative? It's an alternative because it says more. Right? It does not have an equal sign in it. So more than 7. Now, what I always do in my own mind is I start writing as I'm reading more than 7. Oh, greater than 7. But wait, does that work here? Well, let's see. If you lose weight, your after reading will be smaller than your before reading. So you're going to get negative numbers, right? So more than 7 pounds lost means you're less than negative 7. Right? So, and this is a relatively simple thing, but it always throws me for a little bit. And I got to think it through. So I always stick numbers in. Okay, what if somebody comes in and they weigh 150 pounds and they lose 7 pounds? So this is their before. They weigh 150. Then they lose 7 pounds. What do they weigh? 143. So the after is 143. Now if I take 143 minus 150, I get negative 7. Right? More than 7 pounds loss would be less than negative 7. Further away from 0. Right? So think about a number line. If the null is true, there's no difference. So the difference is 0. Negative 7 is over here, and further from the null would be less than negative 7. So if you write it out this way, mu2 minus mu1 right, is less than negative 7, what would the null be? Greater than or equal to negative 7. Right? But these are paired data, so we don't write our hypotheses in terms of mu2 minus mu1. It's the differences. So we replace this with what? Mu d. So mu d. So the hypotheses then are mu d greater than or equal to negative 7 and mu d less than negative 7. Okay? So to me, that's the hardest part of this whole paired data two-sample means problem, is getting it set up. Once I do it, I get it set up, then I just got one sample of differences and I do a one-sample t-test and I'm good. I'm done. All right? So there is the answer they came up with, arguing the same way that we just argued. Okay? Now, unfortunately, we get stuck by the Hawkes system again, just like on the last couple of times, dealing with rejection regions. I don't like to do hypothesis tests that way. I like to do them with p-values instead of rejection regions. But you're going to have to do it on the homework. I've already looked ahead. This is the formula for a test statistic. That should look familiar. We've had that before. Test statistics are set up so that it's the sample point estimate of the mean difference minus the population value, well, the hypothesized value, right, divided by the standard error. So the standard error is the S sub D. Now what is S sub D? Good. Standard deviation of the differences. So after you take the differences and you have them in L3, you do one var stats on L3, you'll get, the calculator will call it X bar, but that's D bar, and it will call it SX, but that's SD. It's on the differences, right? And then what is N? What'd you say? Sample size, and it's number of pairs, right? It's not the total number of data points, because you got 2 data values for each person. It's the number of people or objects, so number of pairs. Okay? So that's easy enough. This is what's not quite so easy, and that's rejection region. I haven't been teaching this, but you're going to have to learn it for today. So we're going to go through this first example and show how this is done. There's nothing complicated about it, but you got this from me last time by email, right, to get you through the homework. Does anybody have trouble getting through that homework? On the 2-SAMP t-test, it's the same idea. You get a t-test statistic and you get a critical value. It's just a different way of computing the test statistic, but the rejection region idea is exactly the same. Okay? So if it's a left-tailed test, then you're going to get a negative value for your test statistic, probably, and you're going to have a negative value for your t-critical value. So this is test statistic, this is critical value. And it is critical that you keep those two things straight. There's 2 t's going on here, and people get them confused, and it's easy to get them confused. One is the test statistic. That's the value of t from your sample. The t-critical value is the value of t. The critical value is the cutoff for how extreme your t is. If it gets less than or equal to negative t, then you say, I'm going to reject the null. So that's called your rejection region. Right? So let's draw a picture of it. Here's a t distribution with n minus 1 degrees of freedom. If the null is true, this thing will be centered at 0. Let's say I'm doing a left-tailed test. Most likely in a left-tailed test, my observed value of t will be a negative value, and it'll be over here less than 0. Right? Left tail. The critical value we label as t sub alpha, and it will also be a negative value. If my observed test statistic is further away from 0 than the critical value, then I'm going to reject the null. Okay? So you get t. There's no minus sign in front of t here. I put it there because it will be a negative number. But when you write it as t, t is negative, so it doesn't show up in the formula, but it'll be a negative number. And then is that even more negative than the critical value? For a right-tailed test, they're both over here. So it's, is your t bigger than the critical t? Now what happens in a two-tailed test? Why the absolute values? Because you have to deal with both a negative one and a positive one. So you take the absolute value and just go to the positive side. But look what happens to your alpha. You split it in half. Half of the alpha goes in the upper tail, half of it goes in the lower tail. Okay? Okay, so here's an example. We're going to figure out rejection region and all that stuff for this problem. The standard course at a local defense driving school includes several films depicting violent car crashes and graphic pictures of injuries sustained in these crashes. The driving school has shown that these videos for many years, believing that they reduce the students' average speeds on the highway. A group of concerned citizens who feel that these videos are very disturbing is not convinced the videos reduce highway speeds enough to make a significant difference in highway safety. Did any of you have to do this when you were in driver's ed? Or some of you, I have no doubt, have been to driver's school because you got too many tickets. Yeah, that's what I thought. Right? Do they show you this kind of thing in driver's school? Did anybody have to see these kind of videos? I remember this is actually a true scenario. I don't know that the data is real, but it's a true scenario. Some driving schools do show these things, and they're worried that you're upsetting our kids for nothing. It really doesn't help, right? So the key here is make a significant difference in highway safety, right? Do they reduce speeds enough? So here's the claim. The group claims that these videos reduce a person's speed on the highway by less than 5 miles per hour. They reduce it by less than 5. Right? To test the claim, the citizens install electronic data recorders in the vehicles of 10 volunteers who agree to drive as they would normally for 2 weeks while they record their speed. After the initial driving period, each volunteer watches the videos. Then, the electronic data recorders again record their vehicle speed for another 2 weeks. What is this kind of design called? Each person gets a certain treatment, right? They drive with no video, and then they get the treatment. They come back and they drive after the video. What's that design called? Have I mentioned?
I was going to say it before you did.
It's a crossover design, right? Each subject gets both treatment. That's paired data. So on the test next Friday, there won't be a flashing neon sign that says, hey, this comes out of the section for paired samples problems. You have to read it and go, oh, they're talking about paired data here. They do it one time, then we measure them again after something else. That's paired data, right? So paired data. Now we want to test that claim. Oh, yeah, you had a question. What was your question?
Wouldn't just having the electronic data recorder change their driving
habits? Yeah, I'm glad you said that because I was going to mention that and then I got onto the crossover thing. We won't critique the design of this study, but he just picked up on a serious problem. What's a problem with the design of this study? It's not blinded, right? They agree to drive normally for 2 weeks. If they put a thing in my car and they say, hey, we're watching you, I cannot help but change the way I drive, right? Because that's how I drive, right? So this would not be a good way to actually do this study. You would need some other way of doing it, but it is kind of interesting. They've been doing some recent studies, actual studies on teenagers and texting while driving, and they put cameras in the cars, and the idea, and it worked, leave the camera in there long enough that they kind of forget about it. So the first couple of weeks, yeah, they change their behavior, but then they go back and they start texting again, and even though they know they're being watched, they still were doing it, right? So you can do this kind of thing, but you have to take those considerations in. But anyway, we're going to use a 0.05 level of significance to test that they reduce a person's speed on the highway by less than 5 miles per hour. So the first step is what's step number 1? State the null and alternative hypotheses. Now, I'm not going to have you enter this data into your calculator. We won't take that time. That's how they're going to work it. But they also give us the summary stats we need, so we're going to do it from that perspective. It'll save us a little bit of time. All right, so state the null and alternative hypotheses. Reduce speeds by less than 5. Now, if the alternative is true, right, then what the group is claiming, that's our alternative. The group claims that they reduce it by less than 5. That sounds like I want to write my alternative less than 5. But I got to remember before minus after convention that they use. Before should be, if the after minus before, which one, if it reduces less than 5, this would be what? This would be negative, right? So if it was before minus after, that reduction should be less than 5. But now I got to reverse the order of subtraction, so this becomes what? Greater than negative 5. Oh man, remember algebra? When you have an inequality and you multiply through by a negative and it reverses the order of the sign. So, mu d greater than negative 5. But it helps my mind a little bit to think of a number line. I don't actually draw it out, but think of a number line and say, okay, that's the null hypothesis. No difference at all, right? Or in this case, it's not the null, but it's this 0 represents no difference. And negative 5 greater than that would be closer to 0. So less change in their speed, right? So that was the alternative claim, that there's less change in their speed than what the people who make the video thought. So the people that make the video think what? Less than or equal to negative 5. Okay? So there's our null and alternative hypotheses. Which are shown on the video there. So step number 2, determine which is the right procedure to use. Remember that little tree diagram of decisions? What's the first question you ask yourself? Is this means or proportions? It's a means problem, right? We got speeds and average speeds and all that. It's a means problem. And then is it, what's the next question? One sample or two? It's two samples. We got before the video and we got after the video, right? Next question. Are they paired samples or are they independent samples? These are paired samples. Same subject being measured twice, right? So then on your cheat sheet, after you go through those questions, you know what you're supposed to use. And what are you supposed to use? T-test on the differences. All right, so this will be T-test on the differences. They talk about which distribution. I talk about which function on your calculator. It's really the same decision. Okay? So step 3 is to gather the data and perform the hypothesis test. Remember, with a before and an after or paired data of any kind, it's the differences that matter. So if you remember, we went through a problem where I showed you how to put these in L1, these in L2, and then tell your calculator for L3, make it L2 minus L1. Right? But so we won't practice that today. You don't need to enter this data because they give us the summary stats right here. Okay? So go ahead and get your calculator and go to T-test. Remember, it's a one sample of differences test now. We've reduced it to one sample by taking the differences within each pair. Instead of having two paired samples, I've got one sample of differences. Yes?
I don't know if I wrote it down wrong, but I had differences on t-interval instead of t-test.
You didn't write it down wrong. That's when I drew that t-diagram, we had only done confidence intervals. So now to that, add right below that or t-test. So it's the same tree diagram as before, only instead of everything being interval or int, it's now test, right? So both should go at the end of that. And you have to decide, are they asking me to do a confidence interval or are they asking me to do a hypothesis test? All right, so go into your t-test. The first thing that it asks is mu0.
Or data or stats.
Oh yeah, data stats. Which is it here? We're going to use stats because they did give us the summary stats on this slide. If all we had was the previous slide with the lists, then we'd get those differences into L3 one way or another, and we would select data and then tell it L3. But when we choose stats, it now changes the screen and it asks for the mean, the standard deviation, and the sample size. So what is mu0? -5. You look at your null hypothesis, and that's the number that's in your null hypothesis, -5. And then your calculator says x bar. We called it d bar here, but it's the sample mean. So x bar is -3.57, and the sample standard deviation, which your calculator calls SX, 2.352993. Go ahead and enter all those decimal places. That's overkill, but we want to match what they got. So, and then n is, anybody remember what the n is? 10. Right. Or was it 15?
It's right there on the board.
Oh, it is? Oh yeah, right here. Yeah. Okay. And there was a 15, and was something we were looking at a minute ago, but okay. And then the next thing it asks is, what is your alternative hypothesis? So it has mu and then a colon, and then you pick either a not equal symbol, a less than symbol, or a greater than symbol. And now you just go back over to where you wrote down your alternative and pick whatever you got there. So pick the greater than symbol, hit calculate, and go ahead and tell me what you get for a test statistic. 1.922. Give me one more place to prove we did more than what's on the screen.
1.9218.
9218, okay. And then give me the p-value. 0.0434. So doing it with the p-value method, which is how I'm going to have you do it on the test next Friday, you're ready to make a conclusion, right? You're going to say, oh, that's less than our alpha of 0.05, so we reject the null. So there is sufficient evidence to say that the alternative is true, so they are changing their speed by less than 5 miles per hour. Question?
You forgot to throw in your alternative, the less than for like the leading set. Would you get the same answer if you plugged in?
You sure would. If you didn't flip it around and use their direction, you would have hypotheses mu d greater than or equal to +5 and less than +5. So make sure you would have a positive for your mu0, not a negative. But then your d bar would have been a positive 3.57, and you get exactly the same p-value. Okay? Question?
I got something.
You got something different? Then you did something wrong. No, I'm just kidding. I actually, since this matches what's on the screen, I'm pretty confident. What did you get?
Okay, it's greater than 0.
Did you use a negative here? Got it? All right. Okay, now, to do this with the rejection region, remember, let's go back to this slide that had the rejection region thing on it. Somewhere. Right there. So, which do we have? Left-tailed or right-tailed? It is right-tailed because we want to be greater than something. You always look at your alternative to make that. And this is a confusing slide because it's got an or equal on it, right? But that's because this is rejection region, not the hypotheses. We're going to reject if we're greater than or equal. So if we're out in the right tail, right? This is a right-tailed test. Okay? So if it's a right-tailed test, then I need to get a critical value T sub alpha. So in my drawing here, I need to know this cutoff T sub alpha. And my alpha is 0.05 for this problem. So what is that number? T sub alpha equal. How do I get that number? What? Not T interval. The I in V doesn't stand for interval here. Inverse T. That's right. Inverse T function. So if you have it on your calculator, you use inverse T. And what does the inverse T function need? It needs two things. What'd you say? Area to the left, right? Well, if I have 0.05 area out here to the right, how much area is to the left? 0.95. Now you could also put in there 0.05, just put alpha in there, and you'd get a negative on the answer, but it'd be the same number. And then you just know, well, I'm in the right tail, so I ignore the negative. Right? So inverse T, 0.95 or 0.05, and how many degrees of freedom? 9. We have a sample size of 10. Our degrees of freedom is 1, or is n minus 1, so it'd be 9. And that gives you what? 1.833, right? To 3 decimal places? Okay? So what is my rejection region? My rejection region is T greater than or equal to 1.83. So the rejection region is T greater than or equal to 1.833. Now what about our T? Are we in the rejection region? Yeah, we had 1.922, which is greater than or equal to 1.8, so we're going to reject. Right? But we already decided that looking at the p-value. But here is that. So we will reject the null if t greater than or equal to 1.833. Now in the Hawk's learning system, you can either use the inverse t to get that t critical value, or you can click on the tables button and it'll pop up the t table. Well, it'll pop up a list of tables and you got to pick the t table, and then it'll let you navigate to 9 degrees of freedom, and then it'll say area in, does it say area in 2 tails or area in 1 tail?
Some of them have
Or it lets you choose, right? So if you're doing a 1-tailed test, you'll say area in 1 tail. If you're doing a 2-tailed, pick that one. And it makes it pretty easy to get that number. Right? And on the test next Friday, if you don't have this inverse t function, I will have t-tables from the book to give you. And then you could just look it up. Okay? So step 4 is to draw the conclusion. We've already decided we're going to reject the null. This is the picture that I have here with the 2 put on there. This is the observed, or the critical value, 1.83, and our observed value for t is 1.922. Since it's further out in the tail, you're going to reject. It's in the rejection region. All right? Okay, now I want to do this example real quick. This is from your data that you collected when we did this for confidence intervals. We did paired data. Remember we did the experiment on standing versus sitting heart rate? You should remember that. That should have been a life-changing experience. Here was your data. Again, I'm not going to make you enter all this. I'm going to give you the summary statistics, but I want you to work this problem on your own. What we're going to do is do a hypothesis test now instead of a confidence interval. But let's review that confidence interval. So, first of all, here's some summary statistics. The point estimate of the standing mean was 75.18. The sitting mean was 68.18. You subtract them, you get the mean difference. So this is X, or this is D bar. D bar is 7. Now it's just pure luck that we got an exact integer there when you round to 2 places, right? I wouldn't have expected that, but so don't think it's always going to be a nice integer. And then we had the standard deviation of the differences. This is S sub D, right? We did a 95% confidence interval, and we got 5.19 to 8.81. Does that interval let us make a conclusion about whether there is a difference in heart rate? Why? Because 0 is not in there. The null hypothesis in this case would be, right, the claim. Well, I actually haven't shown the slide that says test the claim, but you'll see it says test to see if there is a difference. Right? So it does let us, so we already know what we're going to get from our answer here when we do it as a hypothesis test. A confidence interval and a hypothesis test must make the same decision. If this rejects the null, our p-value better darn sure reject the null also. If they don't match, you did something wrong. So here you go. Conduct a hypothesis test of this claim. Use a significance level of 0.05. All right? So go. Do it. I want you to do it. I'm going to come around and observe it. As soon as you get done, we've got a little quiz to take. All right? Yes. All right. So I'm going to go ahead and shut the video off. If you're watching the video, the next few slides after this show how to do it. So try it on your own, and then pull up the slides and see if you did it right.